Okay, Laplace transform of the step function. So what we'll do here is we'll define the step function and then see how we can use it to define other functions, shift functions, and look at the Laplace transform and some examples. So this is the step function. It's, oh, where's my pen? There it is. It's 0 until you get to a point A, and then it's 1 afterwards. So u2 of t at t equals 2, that's 2. It takes a step upward from 0 to 1. So we can use the step function to define other functions. The step down function is this, 1 minus u2 t of 1 minus u2 of t. So f of t equals 1 minus u sub 2 of t. And so that equals, well, this is defined as 0 until 2. So 1 minus 0 is 1 for t less than 2. And then this is 1 if t is bigger than 2. So it's 0 for t greater than or equal to 2. And so the graph of that is 1 until you get to 2, and then it's 0 afterwards. So if we take a difference of two step functions, we get it doesn't have a proper name, but I call it the on-off function. So u2 of t minus u3 of t, well, if we draw them together in the same graph, u2 of t is 0 until it gets to 2, and then it's 1. u3 of t is 0 until it gets to 3, and then it's 1. So 0 minus 0 is 0. Between 2 and 3, u2 is 1, u3 is 0, so we get 1 there. After 3, they're both the same again, so we get 0 there. So the graph of this function is this. Turned on at 2, turned off at 3. And we can start chaining those together, right? This is on at 2, off at 3, on at 4, off at 5. So this function is 0 until it gets to 2. And then it drops back down to 0. And then we turn it back on at 4 and off at 5. Whether the circles are open and closed doesn't really matter much, so I'm not going to pay a huge amount of attention to that. And so that's what this function looks like. Now, a square wave goes on at, well, an example of it, on at 1, off at, goes on at 0, off at 1. At 2, it goes on. At 3, it goes off. At 4, it goes on. At 5, it goes off. At 6, it goes on, etc. So that's what a square wave looks like. And so what's the formula for this? Well, it goes on at 0, off at 1, on at 2, off at 3, etc. So this is square wave. You can think of that as being a series of pulses being transmitted to something. So here's another function that you can build using step functions. This function, the graph of it is t minus 1 from 0 to 2. So it's a line that's got a y-intercept of -1. And when t equals 2, it's at 1, which is up here. And so it looks like this. It's 0 up to here and 0 after here. So what that means is that we turn it on here and off there. So what's a formula for f of t? The function is t minus 1. turning it on at u0 and off at, oops, at 2, and that should be minus. And so that gives you this function. And you can develop this into something called the Sawtooth Wave, which is just this repeated over and over again. But you have to keep in the fact the line is moving to the right. So this function is t minus 1. This function is t minus 3. This function is t minus 5. This function is t minus 7. So what's the formula for this? Well, we want t minus 1 times u0 of t, so the on at u0 and then off at 2, plus t minus 3 on at 2, off at 4, and then plus t minus 5 on at 4, off at 6, etc. So it's something called the Sawtooth Wave. Sawtooth waves and square waves are pretty common, just discontinuous functions that you see. So in order to think a little bit about shifting functions, so I have a machine that produces a sine wave. I want to turn it on at t equals 3 and have the output be a sine wave starting with f of t equals 0. So draw the graph. So when I turn the machine on, it gives me this output. And what I want is, I want that output to start at t equals 3. So what do I need to do to get this function? Well, we need to move the graph of y equals sine x, sine t, right 3 units, and turn it on at t equals 3. So the graph of this function is, the formula for this function is, so we're turning it on at t, so u3 of t, and we want a sine function shifted to the right 3 units. So turning on at 3, shifted right 3 units. So decaying exponential. And again, I want to turn on the machine at t equals 5. So decaying exponential is e to the t, so that starts at 1, height of 1, and it decays like this. And that's my t-axis. But I don't want this graph. I want a graph that actually looks exactly like that, but starts at 5. So what does that mean I need to do? I need to shift e to the minus t right 5 units. And that gives me e to the minus t minus 5. And I want to turn it on at t equals 5. So the function, this function here, is u sub 5 e to the minus t minus 5. Good. So what we want to do is, what's the Laplace transform of this thing? So Laplace transform of u sub a of t is the integral from 0 to infinity of u sub a of t e to the minus ts dt. But this is 0 until you get to a. So this is the integral from 0 to a of 0 times e to the minus ts dt plus the integral from a to infinity of 1 times e to the minus ts dt. So this is just 0. And so we have the integral from a to infinity of e to the minus ts dt. And if you evaluate that, it becomes, do that integral 1 over s e to the minus ts, evaluated from a to infinity. There's a limit involved here, but e to the negative infinity is just going to be 0 minus e to the minus as. So that's the Laplace transform of the step function. Okay, so what's a Laplace transform of a function shifted by a step function? So we're looking at these sorts of functions. So if we take the Laplace transform of some function, use of a of t times f of t minus a, so there's a shifted function. And what's that going to be? That's integral from 0 to infinity, use of a of t, f of t minus a, oops, there's a minus sign in there, e to the minus ts dt. And like we did before, the integral from 0 to a is going to drop out because e sub a is 0. It becomes an integral from a to infinity of just f of t minus a e to the minus ts dt. So this can be integrated by substitution. U equals t minus a, du equals dt. What that means is that the limits a, when t is equal to a, that becomes, for u, that becomes 0. And when t is infinity, u is also infinity. So with that substitution, this becomes the integral from 0 to infinity, f of u, e to the minus. Now we have to be a little careful here because we need to substitute in for the t there. And that's u plus a s du. So this part here can break into e to the minus us, e to the minus as. This is independent of t, because so I can yank it out of the integral. We get 0 to infinity, f of u, e to the minus us du. And this is the Laplace transform of f. And note that the integral here is in u, but it's the same form as the integral for the Laplace transform if we had t, right? Changing t and u doesn't matter because the variable that we use when we integrate gets wiped away by the limits. So a transformed function picks up an e to the as, e to the minus as times f of t. So here's an example with a step function in it. How do we solve this? Laplace transform of y prime equals the Laplace transform of 7y plus u3 of t. So this becomes s times the Laplace transform of y minus 1, because that's my initial condition, equals 7 Laplace transform of y plus the Laplace transform of u3 of t. So we get s minus 7 times the Laplace transform of y equals 1 plus e to the minus 3s times 1 over s, because that's the Laplace transform of u3 of t. So Laplace transform of y equals 1 over s minus 7 plus e to the minus 3s times 1 over s times s minus 7. And so what that means here is we need partial fractions. To break that apart. So let us go up here, and we have the Laplace transform of y equals, what does it equal? 1 over s minus 7 plus e to the minus 3s times the quantity, what's our partial fractions now? 1 over 7 s minus 7 minus 1 over 7s. So that's the partial fraction decomposition. So what's that giving us? Laplace transform of y is 1 over s minus 7 plus e to the minus 3s over 7s minus 7 minus e to the minus 3s over 7s. Okay, so some of these are pretty easy to do. This one is just e to the 7t. This term, we have to go back up here and look at the Laplace transform of a step function times a shifted function. So 1 over s minus 7 is the Laplace transform of e to the 7t, but the e to the minus 3s tells us it's been multiplied by a step function and shifted to the right 3 units. So we end up with plus u3 of t times e to the 7t minus 3. Same thing here, right? This is an e to the minus 3s tells us that there's a step function shifted right 3 units. So it's going to be minus, oh, and this is over 7. Minus 1 over 7 there. And 1 over s is the Laplace transform of a constant. So this is just going to be u3 of t. So this function is basically, we at time t equals 3, we turn on these two functions, and that is added to the e to the 7t. Okay, so how would we solve this without using Laplace transforms? So basically what this is without Laplace transforms, you'd have two problems. dy dt equals 7y for, t between 0 and 3, and y of 0 equals 1. And then the second problem you would have is dy dt equals 7y plus 1 for t greater than or equal to 3, with y of 3 being whatever this solution is, evaluated at 3. And that would give you a different initial value problem, and you'd have to solve both of them. But you expect from this term, from the dy dt equals e to the 7y, dy dt equals 7y, that's where this e to the 7t comes from. And this solution to this differential equation that starts at time t equals 3 is going to be e to the 7t plus a constant, both of which start at 3. And that's what we got here, e to the 7t starting at 3, and then a constant also starting at 3. So here's one with a shifted function. So this, to solve this, we get Laplace transform of y prime equals minus Laplace transform of y plus the Laplace transform of u3 of t e to the minus 2 t minus 3. And that becomes s Laplace transform of y minus 1 equals minus Laplace transform of y plus e to the minus 3s, and then the Laplace transform of e to the minus 2t is 1 over s minus s plus 2, because it's e to the minus 2t. So we get s plus 1 Laplace transform of y equals 1 plus e to the minus 3s, s plus 2. So the Laplace transform of y equals 1 over s plus 1 plus e to the minus 3s over s plus 2 times s plus 1, because we divided through by the s plus 1. And again, we're going to need a partial fractions to get us out of that. And so this will end up being 1 over s plus 1 plus partial fractions. There it is. E to the minus 3s over s plus 1 minus e to the minus 3s over s plus 2. So there's our Laplace transform, and it's not too hard to get the hang of this to see what this is. This is going to be e to the minus t. This one's going to be e to the minus t shifted right 3 units and multiplied by a step function. So u3 of t times e to the minus t, but we want to shift it right 3 units, minus, this is an e to the minus 2, e to the minus 2t because of the denominator, but shifted right 3 units because of the step function. So this starts at t equals 3. This is the solution that you just have before the thing kicks in there. So this, right, this is an undamped mass on a spring. No friction. And so that means if we just had y double prime plus 3y equals 0, our solutions would be cosine omega t plus cosine root 3 of t plus sine root 3 of t, because it's the square root of this thing. But what we're doing here is at time t equals 4, we turn on a cosine force. So the physical thing here is we've taken a mass on a spring with no friction, we pulled it out 1 unit and we let it go, and it starts oscillating back and forth. And then at t equals 4, we turn on a force, cosine force, and we want to know what's the motion of the spring when that happens. So Laplace transform of y double prime plus 3 Laplace transform of y equals Laplace transform of u4 of t cosine of 5 t minus 4. And so what we know here is since 5 and 3 are different numbers, we're actually not going to get 5 and square root of 3 are different numbers. We're going to get beats, not resonance. But the beats will only start after t equals 4. So this is s squared Laplace transform of y minus s plus 3 Laplace transform of y equals e to the minus 4s, and that takes care of the u4 of t, times the Laplace transform of cosine of 5t. So we get that. So what we have then is s squared plus 3 times Laplace transform of y equals s, because we have to bring this s over, plus e to the minus 4s s over s squared plus 25. And so that gives us the Laplace transform of y equals s over s squared plus 3 plus e to the minus 4s s over s squared plus 25 times s squared plus 3, because we had to divide through by the s squared plus 3. So what do we have here? 5 over s squared plus 3. No, that's not a 5. That's an s. Plus, when we have to do our Laplace transform thing here. No, not a Laplace transform. We have to do the partial fractions on this thing. And so that gives me 1 over 22 times e to the minus 4s over s squared plus 3 minus e to the minus 4s over s squared plus 25. And so that is my partial fractions. So what do we actually get here as solutions? S over s squared plus 3. That's cosine of square root of 3t. So that's the motion of the mass of the spring without any forcing. That's its natural motion. E to the minus 4s over s squared plus 3. Well, I'm going to multiply that top and bottom by 1 over square root of 3 to get square root of 3 e to the minus 4s over s squared plus 3. And that's a sine term, and it's been shifted by that. So this is an equals, and that becomes 1 over square root of 3 u sub 4 of t sine square root of 3 t minus 4. So that's part of the response to the forcing is this. And the other part of the response to the forcing is, oh, this is all over 22, because this is coefficient out front. And the other part of the forcing is e to the minus 4s over s squared plus 25. Multiply top and bottom by 1 over 5. And we get that. So this is 5 over s squared plus 25. That's another sine term. So we have 1 over 5 times u4 of t sine 5 t minus 4. And that also is times 1 over 22. And that's a times. So these two terms here are the response to the forcing kicking in at t equals 4. This term is the natural response of the system to its initial conditions.